Record is rolling. It is Monday, March 31st. We got 46 days until, ooh, guys, what's on May 16th at 7:30 in the morning? AP exam. Your guys' AP exam. Yeah, I've got 46 days. So I posted some things to Google Classroom. There's some testing information, especially for, oh, guys, I know some of you guys are 10th grade, especially if you're in 10th grade. You're going to need this info right here. I'll point out to you. And then now for everybody in the class, there's flipping physics reviews. So let me flip over to Google Classroom. Here we go, right here, Google Classroom. Right. So start with this. So fast test and FCLE. Again, a lot of 10th graders are taking this, but even if you're not 10th grade, you might be relocated because there's testing in some rooms and you're going to that class. So we got, all right, April 1st, which is tomorrow. Guys, there's testing in this school tomorrow. It's past testing. So if you're testing and this Excel file says where you're testing, if you're not testing, take a look at this file, see if any of your classes are relocated. All right, then 2 weeks from now, April 15, Texter, there's FCLE. So there's if you are testing, and here's relocations if you're not testing. So check out these files in Google Classroom. All right, so you guys go with testing info. Okay. Again, especially if you're 10th grade, take a look at those. Okay. All right, then here's flipping physics review. So here got his actual website and then his YouTube channel here. So got similar content. Let's look at his website real fast. Here's what his website looks like. Now, Unit 8, which is fluids. Remember, AP just made that, or just included that in the exam this year. So, yeah, so this review is new. He's got here, I've got my computer muted, but I'll play a little bit so you guys can see this. So here's his review for fluids. Oh, wait, why is it going so fast? He's just doing it so fast. Okay, but he'll throw a little bit of review on the board. He'll throw some question out there, and then he's got himself replicated 3 ways. He's got like 3 different personalities he's acting out right there, answering questions like your students. So, hey, there you go. Those are pretty good. He's got, of course, reviews for other sections too. Okay. All right, what else? Oh, guys, on AP Classroom. So there's AP created their own sets of review videos. So I did open up all those. Guys, I did assign these as if they're due or something. I'm not going to actually count these for class points, but I did open them up and assign them, so they'd be easy to probably navigate to and find. Okay, I think you guys could probably watch these anyway, even if I didn't assign them. But they're there, so you do open. Okay. But you guys do have an assignment in an AP Classroom. I told you guys about this back on Friday. You guys remember this one? So, guys, what's due 1 week from now? Yeah, these multiple choice questions from practice exam 2, which we probably won't actually get to. I might bump that due date back a couple days, but tentatively 1 week from now. So I think it's pretty good. So what do we got? So today, our main focus is going to be simple harmonic motion. I'm going to finish up a little bit of rotational dynamics from last week, but then mostly we're going to focus on simple harmonic motion, which is like pendulums and springs for the most part. Tomorrow we'll recap fluids. That'll probably take us to by the end of Tuesday. I think we'll be finished with the review for this class, and then the last half of this week. So probably Wednesday, Thursday, Friday. I'm thinking is going to be focused on the FRQs. Okay, guys. There are 3 practice exams. So I think practice exam 3. I definitely want to have you guys working alone, right? Because it'll be pretty similar to the exam that way, right? But these FRQs this week, do you guys want to work on these in teams? Yeah, okay, so we'll do that this way. And then for exam 3, have you guys by yourselves. Okay. All right, so any questions about anything going on? All right, no. Here, guys, everybody got phones away? Guys got your games away, phones away? Guys look up here? You guys got paper out? Guys got notes out? All right, we're doing review, picking up from where we left off. All right, so back on Friday, we almost finished rotational dynamics, but it did have a few more to go. So let's look at these. If you have a ball rolling downhill, now the classic question could be, what's the speed of the ball at the bottom of the hill? But remember, there's 2 kinds of speed, right? There's linear speed and there's angular speed. So how fast is this ball moving? Say, if you point a radar gun at it, which is probably the actual question they would ask, that's your linear velocity, tangential velocity, all terms with the same idea. Okay. But don't forget too that this ball is also rolling, it's rotating, has some kind of angular speed as well. Okay? So how could you solve that? And there's 2 ways to solve it. Actually, the way you're looking at it is probably not the way I would do it because it's a little harder that way. Okay, so here's 2 different ways to do it side by side. Now you could go through torque. so I made a free body diagram here and go through torque and solve it that way. But I would probably recommend it and do it myself this other way through energy. In both ways you get the same way. Now here I'm showing for a basketball. Here's a basketball that basically is spherical shell. Okay. So again, no matter how you do it, you'll get the same answer. And for the basketball, get square root 6 plus GH. Is that okay? So something like that. So let's look at each one of these. See if you guys can figure these out. So let's start with free body diagram. You guys go ahead. Draw an incline. Draw a ball sitting somewhere near the top of the incline. Draw a free body diagram that would get that ball in motion. Remember that, or I should say a force diagram. I told you guys last week. Free body diagram, you locate everything at the center of mass and you locate the torques. Okay. Force diagram, you can just put the forces, but remember the forces are going to be at different locations. And because the forces are acting at different locations, there's going to be a torque induced, and then it's going to speed up as it's rolling downhill. Okay. There's no air drag. Yeah, so no air drag. Don't worry about air drag. There's no air drag. Friction? Yeah, there's definitely friction. Because guys, if there wasn't friction, right, it wouldn't roll at all. Okay? In fact, a detail that would probably also be included in the setup, so your guys' diagrams are looking pretty good. Okay? Is they would say rolling without slipping. So guys, if they say rolling without slipping, is that static friction or kinetic friction? Static friction and only static friction. And is the frictional force taking energy out of the system, or is the friction force not doing any work on the ball at all? Yeah, so it's not actually doing any work. Right. Yeah, it's it's only inducing a torque, right? So this friction force is a static rather than a kinetic friction force. So it's a static friction force, and it's inducing a torque, right? But it's not actually doing any work on the ball. It's not taking any energy out of the ball. Okay. So here you go. You guys came up with a weight through the center of mass of the ball. You guys came up with a normal force acting at this edge and also a friction acting at that edge. You guys got that? Okay. All right, and the setup would go something like this. All right, so if I do, if I do r sine theta, that could be, and then I multiply that by this mg. So mg r sine theta. There's a few ways to think about how you get this formula, but this is the torque that's induced, right? So we've got R cross F, right? Now remember, there's actually two forces going on. So whichever one you think is in terms of, I have in terms of the weight here. So mgr sine theta. Okay. And you guys remember also net torque is I times alpha, and this torque we're going to call it the net torque. Right? So these would be the same thing. Okay. Now the tricky part is that if you use this method, you have to. You guys remember parallel axis theorem, right? Which actually filed that poster away, but parallel axis theorem. You have to use this method, but you don't have to use parallel axis theorem on the energy method. Okay? That's one thing that makes this method a little bit harder. Okay, and that's where this 5/3 come here, and I made it orange to make it really stand out. But you guys see this I? Now for a basketball that's spinning on your finger, it's 2/3 mr squared. But if it's rolling along the floor, you add another mr squared because it's actually rotating about this point at the edge. Okay. Right? That's where I'm getting the 5/3 from, because it's 2/3 plus an additional 3/3. Right? Is there any question where the 5/3 comes from? Right? Yeah, this is from parallel axis theorem. Okay. Right. And then you do a bunch of algebra. Now, remember, some of these variables are connected. Like I got here. I know. Maybe skip a step here or there, but I know this basketball has some linear speed, but it also has an angular speed omega. Are those related to each other? The linear speed v and the all right. So what is that connection? I could say omega is equal to what in terms of v? Yeah, v divided by r, where r is the radius of the basketball. Okay. So I would have substituted that out at some point if that had shown up at all, so that I can get the answer all in terms of v. So this could show up. Also, how about angular acceleration alpha? What is that equal to in terms of linear acceleration? A divided by r. You can also rearrange this. So if you had to substitute the other way, you could do E equals omega r, A equals alpha times r. Right? If you had to cross multiply. Right. Also, do you guys remember? Let's do the third kinematic formula. You guys remember V final squared equals V initial squared plus 2ax. You guys remember that one? Right. And if the ball starts from rest, you could just let that term go 0. So the speed it picks up to the linear speed, the tangential speed picks up to squared equals 2ax. Oh. Okay. And in this case, if the distance of travel is x is actually the length of the ramp L, I could just call that L instead of x. Is that okay? Okay. Right. Then if you solve for this A, what do you get? Can you guys do some algebra? Solve for A? What does that look like? Yeah, b squared divided by this 2 and this L. Be like that. Okay, guys up. Okay. And do you guys see how that basically fits into this brackets right here? So okay. I was trying to fit so much on a page, so I made it skip a step here or there, but that's with this A. This A you replace with b squared over 2L. This is where it comes from. Okay. And now this R is still here, so that's why that R still shows up right there. Okay. So it's all little steps there. Okay. All right, so you guys go with this one? All right. Really, the best way to solve it with this method is just to start with a blank piece of paper and just solve it from scratch. But I mean, this is what the answer you should get for a basketball. Okay. But really, the easier way to solve it, and the way I would do it myself, is with this energy method. So let's do it this way. All right. So same scenario, ball roll downhill, but let's do this framework and see if you guys can set up the next step using this method, using the conservation of energy method. Okay. What type of energy turns into what type or types of energy? Can you set up that equation? Make sure everybody got paper here. You guys all right, everybody's got paper. All got paper. That's good. That's all right. All right. All right. Yeah, see, some of you guys are getting this. So here's what type of energy at the top of the hill? MGH. Okay. And by the time it gets to the bottom, it has what and also what? Yeah, translational kinetic, but also rotational kinetic. Ah, there it is. All right, so that type of energy turns into both of these. Okay. But guys, these two terms are not exactly independent of each other. Is this I related to this M? Yes. Yeah, however massive the ball is also plays into its rotational inertia too. Okay. So we could probably do a substitution and factor out the M. And in fact, do you think the M is all going to end up canceling out by the end of this process? Yeah, because it's definitely here, and it's sort of buried in this I also. Okay. What about this V and this omega? Are those related to each other? Yeah. Yeah, in fact, that's what we were just talking about right here. In fact, this could be a substitution point right here, couldn't it? Okay. Okay. All right, so let's do that. Instead of this omega, let's call it V over R. Now that's being squared, so it's combined with this V squared. And this I know for a basketball is 2/3 MR squared, but that would be given to you. So you can substitute in the 2/3 MR squared for the basketball. And remember, this method, you don't have to use parallel axis theorem. So that's one nice thing about this method. There you go. So I put in orange 2/3 because that pertains specifically to a spherical shell like a basketball. Make that really stand out. And this omega, substitute in V over R. Okay. Again, the best way to solve this is blank piece of paper, solve from scratch. We got so much class time, so I'm just going to move this ahead a little bit. But you guys see that the M shows up there, and there. So I have three algebra terms. They all have the M in them. So the M's going to end up canceling out. The R also ends up canceling out as well. The radial size of the ball. And if you solve for the speed V, it ends up being the same thing, the other method. Okay. There you go. There you go. It's linear speed. All right. Okay. And if it was not a basketball, instead of the 6/5, like if it was a bowling ball, a solid sphere, I think the solid sphere works out. I forget, but it's not 6/5, it's something else. Okay. Should know. All right. And then if you have a roll race, so what's going to beat everything is the hockey puck on a one frictionless lane. So I have one lane that's frictionless. And everywhere else, there's definitely static friction to induce rolling. Otherwise, they would all tie. Because if this is all frictionless, they would definitely all tie, wouldn't they? Because there would be no rolling at all. Okay. All right, so a hockey puck's going to win. Okay. Oh, and guys, definitely, what's the speed of a hockey puck at the bottom? Square root 2g. Yeah, square root 2gh. Where here's your h, right? Which you could solve for in terms of this L times sine of this theta if you had to, right? H is L sine theta. Okay, so square root 2gh. Okay? And all these other ones are going, well, not as fast because some of the energy goes into making them rotate. It's conservation example. So remember, they're not losing energy; it's just being diverted into rotational a little bit, right? Okay. Now, AP would probably phrase this as these are all equal mass and all equal radius, just to really simplify it. So you could definitely straight up compare rotational inertias of these. Okay. But guys, even if these aren't the same mass, and if they aren't the same rotational inertia, do they still finish in this order? Or, sorry, I meant, yeah, if they're different masses and different radial sizes, yeah. So what really matters is how the mass is distributed. Okay. Guys, suppose these are both solid cylinders. Would both of these tie if they're both solid cylinders?
Yeah.
Yeah, they would both tie because how is the mass distributed? Okay. All right. All right. So that's all the rotational dynamics. We just didn't quite fit these in last week. So you guys get with rotational dynamics. All right, let's go into harmonic motion, right, which is mostly two scenarios. Right, you get pendulums, you get blocks on springs, and yeah, there's other scenarios they could squeeze in. I've seen them put like ice cubes and glasses of water bouncing up and down. Right. So, you go time period for a pendulum back and forth. If this was a free response question, I've seen them also include this detail, like in the write-up. Right? Make sure this data is small, maybe like less than 15 degrees. It's related to here. What this is actually related to is small angle theorem. You guys know? Right, let's do this. I think I may have mentioned this once before. Small angle. I think they call it a theorem. Right, whatever. Okay. Is that as long as theta is small, then what is sine of theta equal to? As long as theta is, let's say, like less than 5 degrees or something. Okay. Do you guys know what this is? Okay. Oh, and I should say this only works for theta must be in radians for this to work. So let's try this on the calculator. Okay. Change your calculator to radians because this doesn't work in degrees. This only works in radians. Okay. And let's do sine of what's a small angle in radians? Maybe 0.1 radians. That could be fairly small, right? 0.1 radians. Okay. Okay. Maybe it's probably a wedge about this big. Okay. So what is that? 0. Oh, interesting. You guys see sine of 0.1 is basically 0.1. That was weird. What about 0.031415? Just something crazy. Right? Sine of 0.03 something. It basically is 0.03 something. You see that? So sine of theta is basically equal to theta. Okay, as long as the angle's small and only if you're working in radians. Okay. So how does that relate to this? Well, if I take sine of this angle, isn't that basically this distance right here? Right? And this pendulum swinging back and forth, its lateral distance from this equilibrium point is basically directly proportional to the angle, as long as this is true, right? As long as you're working with small angles, okay? And that's what puts it into a harmonic motion category. So harmonic motion kind of follows like Hooke's law, F equals kx, where the restoring force is directly proportional to the distance that it deviates out. Right? It's definitely true for springs, and here it's basically true for small angles. Okay. So how about this, guys? What if you had two pendulums and one was had a length that was 9 times the other? Because if you have 9 times the length, what happens to the time period? 3 times. Yeah, because you slip a factor of 9 under that, or next to the L right there. It's underneath the square root. The square root of that factor of 9 is 3 times, isn't it? Okay. What if you had pendulums on 2 different planets, and one planet had 9 times the gravity? If it's 9 times the gravity, it's going to be swinging back and forth really slow or really fast compared to Earth. Really fast. So if you turn up the gravity, right. In fact, if it's 9 times the gravity, it'd be what fraction of the time period is swing back and forth? 1/3, right? Throw a factor of 9 on that G, right? Square root of 9, it's in the denominator. Yeah, it's a third of the time swing back and forth. Right? So it's definitely going back and forth with a greater frequency, like faster, even faster with it. Okay. Right. So of course this formula is of course on your equation bank. Okay. We're talking about like these formulas right here is what we're really focused on pretty much for us today. Okay, these right here. Okay. Got for block on spring, got one for the pendulum. For this. Okay. Next here. Oh, you guys have had a lab on this. Okay. I had you guys make these graphs. Let's do these graphs. See if you guys can get these from scratch. So you guys set up 4 sets of axes. 4 sets of axes. He's going to get these. Okay. So the scenario is pendulum. Right. You draw a picture if you want. Right. So it's going to swing back and forth, back and forth, back and forth. Right. Got some mass here, got some length here, got some angle here. It's in a gravity field. Okay. Some of those variables might matter to some of these graphs. Right. And the graphs are going to go, let's do time period as a function of mass. T is a function of L. T is a function of theta. And let's do leave the last one blank for a moment. All right. Okay. Guys, let's get some units for these variables. Because if you just have the variables and some numbers marked, then it doesn't mean anything unless you have some units. So what could time period be measured in? Seconds. So it goes there. So I guess all these vertical axes could have the unit seconds, time second. Mass could be measured in what? Yeah, kilograms is a good go-to. Length could be measured in meters is your base SI unit. And theta, this could be degrees or radians. So maybe I'll just pick one and throw it on here. All right. Guys, go ahead and make those 3 graphs for that scenario. Okay? So this is a lab you guys did. While you guys are getting those, if you need a little hint to frame how to think of this. This first one, T versus M, says if you change out this mass, if you start with small masses, then you get a little bit bigger mass, and then bigger masses. Okay, how's that affecting the time period to go back and forth? And that's what time period is, right? It's back and forth. Okay, so you start, say, at the far left, you go to the right, and then back to the left again. Okay, however much time that is. Okay, this graph, T versus L, if you make the length of the pendulum longer, what happens to the time period, and what shape graph does that make? And then if you change the starting angle, maybe this is some data original, right? So like if you go 10 degrees, 20 degrees, 30 degrees, right? And then see how much time, right? See what those graphs look like. All right, we got Alex got them, Hector got them, Landon got them, Hans got them. We got close. What's there? All right. We got Isaac got Ray got not yet. Alec got Hey, Jane got getting there.
Yeah, it's just linear.
So you guys are getting there.
Yeah, that would make sense for it to change.
Close. Let's got these. Close. Okay. Some of you guys are close on some of these. So, guys, all right, let's put them together. Here, maybe we should switch each color to make the graph stand out. Okay. So, as you make this mass heavier, what happens to the time periods going back and forth? Yeah, it stays the same, right? If you plotted a bunch of points, it would look like this. Okay. Oh, we're assuming a negligible mass string so that the length of string isn't changing. That was one consideration. When you guys actually do this in real life, if you hang on this one versus this one is volumetrically larger. So the center mass moves physically. It makes the string a little bit longer. So it wasn't exactly flat on when you guys did the lab version. But if you controlled for that, it would look like that. Right. Now, if you make the string longer, does it take more time to swing back and forth?
Yes.
Yes, but what curve shape did that make? Yeah, it's like a square root looking graph, which is a sideways parabola. Yeah, it's like a square root sideways parabola. Okay. Again, here's the formula. If you want a formula to map, you see time period is proportional to the square root of L. That's what this is. Time period is proportional to the square root of L. If you make an exact equation, you got 2 pi divided by square root of G would be like out in front. Okay. Okay. How about if you change the starting angle? Guys, if you pull this to 10 degrees and it takes some time to go back and forth, you pull it to 20 degrees. Ooh, is it the same time to go back and forth? It is. So 10 degrees takes some time. At 20 degrees takes the same amount of time. Okay. You go 5, 15, 25. Yeah. Just so no relationship. Okay. Again, you guys notice the ones with no relationship. You guys see that those have or don't even show up in the equation. I don't see mass in this equation. I don't see starting angle in this equation. Right? It's not related to the time period. Okay. Now, the length of the string is, and gravity field also is. Right. Right, so you guys give those? All right. Now, how about this last one? What if I wanted you to take the time of the length and manipulate one or both of those to force us into a linear graph? Now, this one, there's multiple ways to do it. So let's ignore these two. So how can I take this graph on the right, T versus L, and linearize it? I have to manipulate one or both of the axes. There's multiple correct answers to this. What's one way? Aha. If some of you guys get that right. All right, what can you put on the axes to force that to linearize? And there's multiple correct answers. Right, yeah. Okay, so seeing some good ones. Okay, so one way you could do it is, what if I left time in seconds on the vertical? Now, if I did that, what should I put on the horizontal? Square root of L would be a good choice. Some square root of meters. Okay. Or if I left L alone, I could square the T. You do that. So that would be another way to do it. Okay. Actually, speaking of that graph, let's see if we can get some information out of that. Let's say you go to an alien planet. You guys ready for this? So alien planet. And the question is going to be, what is the gravity field? Okay. All right. And so you do, let's go T squared versus L. So time squared and second squared versus L in meters. Okay. Now again, what shape graph is that going to be? Yeah, linear. Oh, I think I forgot to show you guys why that would be linear. Okay. Because you can square both sides, right? And this would be T squared, and then square root of L squared is just L. Okay. And then all this other stuff is constants. So yeah, they definitely lined up in a straight line. Okay. And let's pick one of these points. Let's say this one. Oh, notice it goes basically through the origin, so that's nice. Okay. Let's say the time squared and second squared is like 4.7, and the corresponding length is like 0.61 meters. Okay, 61 centimeters. And so more than half the meter stick. Okay, this pendulum swings back and forth. Okay, so you guys know it's a pendulum, some L length. Okay, the mass of the bob doesn't matter as long as it's significantly more than the string. Okay, guys got stopwatch, T, time period. Okay. All right, so I'll solve it. You guys solve it. See if we can get the gravity field out of this. What is the gravity field? Okay, I think I got the answer. I'm gonna write down here. It's right underneath this dog ear, but I'm gonna double check, make sure I got the right thing. Yep. All right. I got the right answer. Okay. Walk around and see who's got the right answer. Okay. Oh wait, show hands. Does anybody think they got it? They got the answer? Yeah, what you got? No, I got more than that. What you get? Hans got it. Who else gonna get this? By the way, there's a really good chance you're actually going to get this exact question on the AP exam. This would be a really good multiple choice question. I bet you're going to get this question. Okay. Who else got it by now? I got more than that. That's too much. Give you guys a little more time. I want someone else to get this. Ooh, no, it's more than
I got the equation just now.
if you think you got the answer, you could check, or if you had multiple choice and you didn't know how to solve it, could you take the multiple choice answers and plug them back into the equation on the equation bank and just see which one gives you the correct? Maybe. Yeah. So, guys, time period. No more than that. Time period equals 2 pi times the square root of L over G. Right. So that's the formula everything relates to. Here, I'll write that too, because of course you would have that on the equation bank. So it would say time period of a pendulum equals 2 pi times square root of L over G. Okay. So something related to that. Okay. Taking one more trip around the room, see who else got this. Nathan got it. All right, so we got all right, I got it now. And so we got Hans got it, Nathan got it. Let's see who else got this. Nah, it's bigger than that. All right, how about Jane got it. I got 3 winners.
That's
Okay, so let's do this one. All right, what I got, what some of you guys got was 5.12 meters per second squared. That's what I'm looking for. Okay, so it's about and guys, what is that compared to Earth gravity? Yeah, that's half of Earth gravity. So you could boing, boing, you can really jump around on that planet. Okay. So, got this point here. Okay. Might be different ways to do this. Okay. So, here, just to pick one method. If I want to make this graph, if I want to manipulate this equation to sort of match this graph, how can I do that? So I see a t squared here. Maybe I should go ahead and square both sides. Can I do that? Can I square both sides? So here, I'll start from the beginning. Time period equals 2 pi square root L over G. But if I square both sides, that's going to be t squared equals, and I got a 2 pi quantity squared times L over G. The square root went away. Isn't that true? You guys hear that? Okay, you definitely put this in your notes. Okay, so only 3 guys got this. Okay. Now, if I want to match this to my graph, I have a y-axis versus an x-axis. Here's my y-axis is t squared. Here's my x-axis is L. And everything else is constants. Right? The gravity field of the planet is pretty much constant for that planet. So I'll go time period squared equals, I'm just going to take the 2 pi quantity squared over G and shuffle that over, put that, wouldn't that be the slope of that graph? Wouldn't it be? Isn't that the slope of that graph? Right? That is the slope of that graph. Okay. Okay. So this bit right here is equal to, well, this slope right here. Okay. And what is that slope? So I can say the 2 pi quantity squared on G is equal to the slope of the graph. Okay. Which is basically 4.7 over 0.61, and then all the units. Okay. So that's 4.7, that'd be square seconds, over 0.61, that would be meters. Okay. Is that right? Okay. Give you guys a minute to digest that. Put that all on the screen there. Okay. Okay. All right. So you guys good so far? Okay. Not the only way to do it. It's just one way to think about it. Okay. If you want to plug things in a little bit different way. Okay. Okay. All right. So now what? Well, I'm solving for this G. So maybe I could cross multiply the G and then take this fraction and invert it, multiply on the other side. So G is going to end up being, so cross multiply that, shuffle that over there. So I got a 2 pi quantity squared, and then times 0.61 divided by 4.7. This would be meters, this would be second squared. Okay. Well, nice thing about keeping your units through your proof is that, hey, look at that. Gravity field is going to be its own number of meters per second squared. Whoa, lo and behold. Look at that. So now what? Let's do a 2 pi in parentheses, square that, times 0.61 over 4.7. Okay. So I'm getting gravity field is 5.12 meters per second squared. Okay. Now, if you chunk this down into smaller steps and you were rounding a little bit, then like if you got something a little bit smaller, a little bit bigger, AP would still take it. Right? They just want to see that your process is right. Okay. So I'll get that. Okay. Now let's take that and let's check our answer, because that was a whole process to get there. And yeah, there's different ways to get to there. I just showed you guys one way. Let's take that and plug it back into the original statement and see if it matches the coordinate on the graph. So I go 2 pi, I'm going to get a square root. I need what, L over G. So back on the graph, looks like the length was 0.61 meters. So 0.61 meters. If it said 61 centimeters, you would definitely put it in meters, just like that, 0.61 meters. Then divide by G. Now here's where we're going to plug in the answer. 5.12, that's meters per second squared. What we get from that. And so that's 2.16 something seconds. So 2.7 seconds. Okay. But the time in seconds does not actually show up on the graph. It's the time squared. So, okay. Right. So I'm going to take that, square it. So I'll just say squared. So answer squared. You guys, when I hit enter, what number has to show up on the screen? If I got this right. Yeah, 4.7. Has to be 4.7. Right? See what it is. Oh yeah. Oh yeah. 4.7. Yeah. So check the answer. Of course, you guys have a time constraint on the the exam. So when you're doing all these practices, you definitely get a good feel for how much time. I know this next practice exam, multiple choice, I'm leaving it for you guys to do for homework. But if you have a timer, you can keep track of see if you can do it within about 90 minutes. That's what they give you. And so you guys get on that linearization. Okay. How about let's do one more linearization for this pendulum. Is what if you want to force the graph to linearize so that the slope is exactly equal to G? Okay. Again, this one there's more than one correct answer. You know what? I'm gonna make 2 sets of axes. Let's do 2 correct answers on this one. You think of immediately of 2 different ways to do this, right? Even though there's more to it. Okay. So here's a scenario: you want to linearize the graphs so that the slope is exactly equal to the gravity field of the planet. So these are definitely both going to be linear graphs. Okay. What exactly can you put on those axes to make those linearize? Okay, for a pendulum swinging in a gravity field. That's on L, on gravity field, whole thing. Okay. Okay. Walk you guys through this one. So I know time period equals 2 pi times the square root of L over G. Okay. Now, right away, I see I can take the square root of G, I can move it over. So I got 2 pi divided by the square root of G, and then times the square root of L. Okay. Guys, is that basically y equals mx? Y equals slope times x, y equals mx right there. Right? Right. Okay. Right. So that could linearize. So that's one of my answers. I could put time period in seconds on the vertical axis. I could put the square root of L in some number of square root of meters on the horizontal axis. Okay. And if I do that, see if you guys are following. What exactly is the slope of that line? Oh, you know what? I'm being silly. That's not what I asked. I'm so sorry. We got to make this G, don't we? Oops. So let's do a little bit more. Let's do a little bit more. I bet we can start from this. So, whoops. Okay. Let's somehow get this G in place. Okay. So, well, I don't want square root of G. I definitely want G. So let's square both sides. Let's do T squared equals 2 pi quantity squared all divided by G. This is all times L. Okay. How about, can I take this G, cross multiply it? Okay. And that'd be like 2 pi quantity squared L equals G times T squared. So I could do that too. Okay. Okay. All right. And this would answer the question I actually did ask. Oops. Okay. So here's your y-axis. Here's your x-axis. And here's your slope. Okay. That's what you want. Okay. You go fix my graph over here. Scratch out whatever I had before. Okay. Okay. All right. So on the vertical axis, I'm gonna put 2 pi quantity squared times the length. Now this would be some number of meters. Okay. And on the horizontal axis, I'll put time period squared, that'd be in square seconds. Yeah, and that would give me a slope that's equal to the gravity field of the planet. That would do it. Okay. Okay. The problem with what I had before was that, sure, it linearized, but the slope wasn't G. Okay, but you have to do all these steps, and now slope's equal to G. Okay. Or, again, there's more than one way to do this. Could I take the 2 pi quantity squared and divide it down and combine it with the t squared? So let's do that instead. So if I do just plain L equals, and I want the G to be locked in place in the slope location, right, then what about all this? I got t squared over 2 pi quantity squared right there. And now this could be your y-axis, and this could be your x-axis. Okay? And the slope is still G. Okay? And so that's the other answer. So I could do length in meters here. I could do, no, sorry, it goes time period squared divided by 2 pi quantity squared, some number of square seconds here. That would still linearize so the slope is still equal to the gravity field. There you go. There's 2 answers to that question. You guys able to do that? Still have? All right. So all these skills we've been doing with pendulums, I have to get to blocks on springs. Blocks on springs is basically the exact same thing as what we just did. Just replace mass and you just replace the length of the gravity field with the mass of the block and the spring constant. Yeah, there you go. Okay. All right, but I still got this one. Right, so you're not going to be asked this, right, but if you remember I is rotational inertia, for a point mass that would be mr squared, in this case ml squared, because L would be the radius. Okay. It does simplify to the equations on your bank, so I want you guys to see that. Okay. All right, so we got block oscillating on a spring. Here you go. Here's your other main scenario. So look at that. Instead of L over G, it's M over K. And otherwise, everything follows exactly what we've been doing for this class. Okay. Guys, does this work vertically and also horizontally? Is that true? Yeah. Guys, whether you have a vertically oriented block that's bounced up down, boing, 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 you guys need a lab version of that. Or if you have a block on an air hockey table with no friction that's bounced back and forth horizontally, those have the exact same motion. Okay? Or for that matter, if you have a block on a 45-degree angle on an air hockey table, right? Or in space, right, where there's no gravity at all, you just pull it back and like go boing, boing. You could be in space, right? And you wouldn't know. Guys, does gravity field show up in this equation? No. So if I bounce this up and down on Earth, and I take this to the moon and bounce this up and down on the moon, it should have the exact same motion. Yes, it will. Yes, it will. Exact same motion on the moon. It's not true for the pendulum, but it's true for the block and spring. Okay, they're good. Okay. Of course, you guys did. Okay, this is a lab you guys did. Okay. Some version of that. Okay, let's do these graphs. So, guys, look at this. Let's start at the one on left. This is actually what law in disguise? Whose law? Hooke's law. You guys see this is F equals KX in disguise. Right? Right, so if you hang a block, right, it stretches its own amount. Now this is equilibrium stretch length. Okay. If you put it into motion, you guys remember just a minute ago we did for if you linearize the graph for the oscillating pendulum. Okay. Well, this would be for the block, and you can force the slope to be K if you want. It's really similar to what we just did for the pendulum. Same thought process. Right? How about X max versus equilibrium? So that's a special poster I have. I think it's right near the end. Yeah, it's this one right here. You guys remember if you start with an unstretched spring and you hang a block on it, you let go. It's going to overshoot the equilibrium, go to some X max, and then it's going to oscillate back and forth while, and eventually come to a stop at equilibrium. Okay. And guys, what is this X max compared to this X equilibrium? It's a ratio of what? 2 to 1. Right. That's all this is shown right here. Right. More importantly, do you know how to derive that? So for the maximum stretch that you set up what framework? Conservation of energy. So MGH, and H is X max, turns into 1/2 kx squared. You can solve for X and get that way. Right? Now for equilibrium, you don't use conservation of energy. You use what? Force equilibrium. Yeah. See Hooke's law in there. Yeah. So force equilibrium. So the force down equals the force up. Okay. Yeah, there's always a 2-to-1 ratio. Okay, your experimental data also showed that was true. Okay. The last ones, how about these oscillating graphs? So I'm looking at this oscillating graph right here. So x is a function of t. I guess it makes like a cosine shape, right? Okay. And then, okay, that's displacement as a function of time. Normally you do cosine, so it starts with some displacement and then moves on from there. Right. Oh, the speed versus function of time goes from cosine to sine, and the acceleration goes back to a cosine and becomes negative. Right? If you want to make these exact graphs, okay. If we got 30 seconds to the bell, I think tomorrow, first thing is I'll bring this one out. We'll do a little bit with this one, and then we'll go on to fluids. Okay. So tomorrow we're gonna do this one, then do fluid dynamics. All right, that is a wrap on today.